All right, let's take a look at our lesson for today. I know we've been waiting for this time. We finally get to talk about the Fundamental Theorem of Calculus Part 2. It's so exciting. There's actually two main concepts that we want to get for this particular portion of the fundamental theorem. One of them has to do with the fundamental theorem being called an accumulation function. Accumulation function. That's talking about basically having a variable on the integral sign. It's an accumulation function. We're going to talk about that. The second thing that we're going to talk about is this, where the integral, well, this is the accumulation part. So g of x equals the integral from a to x of f of t. That means that the derivative of g is f. And that hopefully makes kind of sense to us. Let's go, since I'm looking at you and some of you it doesn't make sense to, let's go back again. If I were to integrate a function, I would get its position, right? We've done that before. We integrate something, we get the position. And so what this is saying is the relationship between these two functions, this one would be the derivative of this one. Right? So I could write it as f of t, that's how it's defined here, or I could write it as g prime, because it is the derivative. That's the relationship that we're setting up here. And this is a very important relationship that carries over into the word problems that we're getting ready to do, and the ones that they love to put on the AP test and the free response part. So this is the accumulation function portion. It gives us a relationship between these that we have to pay special attention to, we have to pay close attention to, so that we don't get them confused. It's very easy to get the derivatives and second derivatives and all that confused. And we're also going to look at this concept where we take the derivative of an integral. That's the other part that we're going to look at. We'll actually look at that one first. We're going to, this box right here has our formulas in it. We're going to figure out what the formulas are. Now, let's talk about the relationship between the derivative and an integral. When we first talked about integration, I explained that they're opposite operations of each other, just like multiplication and division. You know, if I start with the number 5, you know, I multiply by 2 and then divide by 2, I'm exactly back where I started. Right? They undo each other. And that's basically what integrals and derivatives do, is they undo each other. In the most simplest of cases, which is this first one, in the most simplest of cases, basically these undo each other and this single variable drops right here. So this is going to be f of x in the simplest of cases. Now, and I know this is disturbing for some of us. I'm going to do it the long way to show you why that works. Right now we're just talking about the formula. These are all formulas, and I'm going to show you why that works. So the simplest of cases, I would take my variable and drop it in my one variable, x or z or whatever it is, and that would be my answer. Because again, taking the derivative of an integral undoes what the integral would have done. This right here just has to be a number, a constant, whatever, 275, just a number, 2x. Okay. This one, a little bit more complicated, but not too bad. The only difference is the order on my integral sign. To use this technique, the variable needs to be on the top, the upper bound. So the answer to this, the derivative of this integral, do we remember from, some weeks ago how we reverse these? We do the opposite, right? So this rule, the derivative of this integral, is going to be negative f of x, because we would use the negative, do the opposite to change the bounds, to go from a to x. Now this one right here is a little bit more complex. This is if in that location it's not just an x or a z or just a variable. Maybe it's x squared, maybe it's e to the x, maybe it's sine x. It could be anything. Okay, if you have that situation where it's anything other than just a plain x, then you're going to have to do this portion. Now, the very first part of it starts out just like the others, where I take this whatever it is, this expression, and I put it wherever the t's are. But the second part requires us to chain it, and that kind of makes sense. You know, if we have something that's not an x, we typically would chain it. So to do this, when the rule for this is the result would be f of g of x times g prime of x. That would be the rule using, this is the chain rule version. And those are rules. I know for many of us it's like, how is that? That seems too easy. Why do I just put a variable in there? And what I would like to do is show you why with this very first example. I'm going to do this one the long way. I'm going to do the integral first, and then I'm going to take the derivative of the result and show you that we're going to end up with what the rule said we were going to end up with. All right? So using the rule on this one, what should we end up with? X squared. We should end up with x squared. That's what we should end up with. Now, I'm going to, like I said, I'm going to demonstrate this the long way. I'm going to do this integral part first. So I'm going to leave the d dx out. I'm not going to mess with it. So we're going to integrate. So the integral of t squared would be 1/3 t cubed, evaluated from 1 to x. Just leave that d dx out there. So I would do my f of b minus f of a. I would put my x in. I would get 1/3 x cubed minus, I would put my 1 in, 1/3 times 1 cubed. And so now I take the derivative of that. The derivative of 1/3 x cubed would bring the 3 down. We would have x squared. The derivative of 1/3 is 0. And I have what we knew we should have doing it the long way. I still have x squared. Okay? So just to show you, to give you a little bit of comfort, that the rules are appropriate and they work, so don't be troubled about using them. Is everybody okay with that? Okay. On this one, so this really complicated problem is really not that complicated if you know the rule. It's really not that bad if you know the rule. So what the rule tells us, we're going to have to do the chain rule on this one, right? Because x squared is not just a plain x. So we would take the x squared and sub it in. So that's going to give me cosine x squared. Then I'm required to chain it. So I'm going to multiply by the derivative of x squared, which is 2x. And just for clarity's sake, I'm going to put it in the front so that I don't have that out here. Now, why don't we have a plus c with these? Yeah, I mean, so what happened to this c? It went away, right? We're not going to have a plus c with these. So I know some of us have gotten into the habit of putting plus c on everything. Don't put a plus c here where it's not required. All right, our last one on this page, so we're going to, again, use our chain rule. We're going to put in the x cubed, multiply by the derivative of x cubed. So our final answer will be 3x squared over 1 plus x cubed. Okay? So now you understand the cartoon on the front of your syllabus. Now you completely understand what that is. All right? Any questions? Okay. One more slide. So let's go to that. Okay. One more example using the fundamental theorem with the derivative of the integral thing, this guy right here. So let's work one more, and then we will get to the accumulation portion of this. All right, so I'm doing the derivative of the integral. I'm going to take that sine x, and I'm going to drop it wherever there's a t. So this is going to be cubed root of 1 plus sine squared x. Then I'm going to take the derivative of sine. The derivative of sine is cosine. And I'm going to simply multiply it with cosine. And you can leave it like that. Or you could put the cosine squared in front. I mean, however you think it's clearer to communicate. All right, so really, it looks really, really bad, right? It looks really bad, but it's really not. Are we okay with that? Mm-hmm.
Let's say instead of that being sin x, instead of sin of 2x, would that be, would end up as being sin squared of 2x times 2 times cosine of x?
You would have to chain the sine 2x, so it'd be cosine 2x times 2. Uh-huh. Okay, so good question. This was causing confusion earlier also. We're not chaining anything in the integrand. Okay, we're not chaining anything into the in the integrand. We are actually chaining what's on the integral sign. That's what we're chaining. This portion right here is unmoved. You don't do anything to it except put this expression in it. You don't do anything to it. What you're chaining is this. And you're chaining that because it's not a plane X. Okay? All right. Now let's get to the other portion of Fundamental Theorem Part 2 that's really, really important. This is a function defined by an integral. Okay, so this is a really, really big deal. Let's interpret what it's saying first. The relationship between f of t and g of x. So f of t, or actually as I sub the x in, f of x is what to g of x? It's the derivative. It's the derivative. So f of x is the derivative of g of x. These are equivalent. That's what it is. All right? That's what this defines it as. That's what it is. That is the derivative. So we are given a picture of f of x. So what is the relationship of this picture to g of x? It's the derivative. This is the derivative of g of x. Okay? We need to be sure to be clear with that relationship because that relationship is going to guide all of these questions, how we answer all the questions. And if the relationship is off, you're going to answer them all wrong. Okay, so we need to pay close attention to this and see what it says. Another thing that we get out of this expression is our starting value. When we find y values, which we're going to have to, y values of the position, we always have to start our integration at 0 because that's what this says. This could have easily have said 5 to x, or 3 to x, or -1 to x. It could say anything. In fact, I can change the whole problem answers by just changing that number. That's how important that number is. Please don't assume that it's 0 always. It's not. This happens to be 0. So that's really important. Now, if this were not here, if this expression were not here, what was our default? Now remember, before we were defined by an integral, we would typically have like a initial condition, right? You were told that f of 2 equals 5 or something like that. And then you could calculate all the y values using that information. Remember that? If you didn't have the initial condition, what did you assume to be true? That the first one was 0. Okay, now that's one technique of solving these. We now have added a third option to this. The third option is we have been defined by an integral. Same procedures. I mean, nothing about what we're getting ready to do is going to be different. It's just starting with a different basis. Our basis is this integral, and we're going to find our y values, I'm simply going to sub this in here, where the x is. For each one of those. I'm going to do an integral for each one of these. Now, it's really important to show the integral. After you show the integral, you can do whatever you want to in your head. Okay? But it's really important to show the integral. You need to get into the habit of showing the integral. That's what you get points for. So, when we calculate g of 0 is going to be the integral from 0 to 0 of f of t dt. Now that took like 2 seconds to write. Now, we know from previous work the zero width interval, right? Going from 0 to 0, what is that integral always going to be? Or going from 2 to 2, or it's 0. So my function value of g at 0 is 0. So now let's do g of negative 1. G of negative 1 is going to be the integral from 0 to negative 1 of f of t dt. Now we're integrating backwards. Okay, some of you may be very comfortable leaving it this way, and knowing that we're going backwards would automatically make it opposite. But in case there's a danger that we would forget, let's go ahead and just use our rule, and let's change the bounds so we integrate forwards all the time. So I'm going to change my bounds. Do you remember how to do that? We just talked about that, right? Negative. So negative 1 to 0 of f of t dt. Okay, so I go over here to my chart. This is my derivative, and I calculate the area between negative 1 and 0. Just right there. So it's 1/2 1 times 2, so it's 1. So it's going to be a negative, where I get the negative from is right here, negative 1. It's dangerous that's a dangerous one, because I find that students would just automatically say, oh, what's above the x-axis, so it's positive. Well, it would have been positive if we had started our integral at negative 1, right? But we didn't. We're forced to start at 0, which means when we go backwards, when we integrate backwards, we are reversed. Okay, that's why we have this rule. If I change the bounds, I do opposites. If we integrate backwards, it's opposite of the way it looks. Okay? All right. So let's do g of 2. G of 2 is going to be the integral from 0 to 2 of f of t dt. So we go over here and we calculate this area from 0 to 2. So that's 1/4 of a circle. Pi r squared is 2. So what is that, pi? Okay, so g of 2 is pi. And the last one that they ask us to calculate is g of 5, which is the integral from 0 to 5 of f of t dt. So now we want to go from 0 all the way to 5. So that's going to be pi, and then this, I don't know what I did, a trapezoid or who knows. It's going to end up being negative 4, this area right there. And so now I have the 4 function values that they asked me to find. Are we okay with that? So it's just a little bit of a change from what we've been doing, nothing too dreadfully different. The only difference is how we are defined. So part B says find all the values of x on the open interval, negative 1 to 5, at which g has a relative maximum. Where do we find relative maximums? When the derivative is 0 or undefined, right? Now this is a picture of the derivative. We have any holes in this picture? No. But we do have a 0. The 0 is at 2. Okay, it's at 2. So let's do a sign chart. Since we're doing relative, I'm just doing the actual critical numbers. So on our sign chart, let's see. Here from negative 1 to 2, we are positive, right? Our derivative is positive. So this is a picture of g prime of x, which we could also call f of x. Okay, these are the same. It's a sign chart for g's derivative. Let's see, from 2 to 5, we're under the axis, so we're negative. So do we have a relative maximum? Yes, at 2. So if it says find all x values, so x equals 2. So relative max, x equals 2, and we have to say always because, justify even if they don't say so, because what? Because g prime of x changes from positive to negative. Not very different, right? We're okay with that. All right, part C, absolute. We did one of these yesterday. Absolute means candidate's test, period. That word absolute should immediately trigger the word candidate's test in your head. Whenever you see the word absolute, you need to think candidate's test. So we need to find absolute minimum using the candidate's test. What are the candidates? How do we find the candidates? Endpoints and zeros of the derivatives, critical numbers of the derivative, right? And we don't have an undefined, so endpoints and zeros of the derivative. So our candidates are, I think so, like we need a drum roll or something. Candidates are g of -1, g of, what did we say? That was 2, and g of 5. Now, if they were nice to us in this part A, they had us find most of that. If they were nice, were they nice? Yeah, they were kind of nice. So g of -1 is -1. G of 2 is pi. And g of 5 is pi minus 4. All right, those are our candidates. And our minimum is going to be, yep, -1. So what does minimum value mean? Y value. Y value. Minimum value is -1 because by candidate's test, it is smallest. Or by candidate's test. No, you can provide extra information. So what you want to keep in mind is timing. You know, every few seconds that you save gives you more seconds on a different problem to work. So it's certainly fine to do extra information. Just watch your timing. All right, the last problem says, part D says, find the x-coordinate of each point of inflection. Oh, goodness. Now they want inflection. What do we have to do now? Second derivative. How do we get to the second derivative with the information that we have? It's the derivative of this picture, right? If we look at this picture, we look at the slopes of the picture, we get the second derivative, right? G prime. So, let's see. See if I can fit it up here. So, G prime, G double prime of x. Okay, G double prime of x. So, we have a positive slope from -1 to 0. Positive, right? It's positive slope. We have negative slopes from 0 to, what is that, 3? 0 to 3, negative slopes. And then from 3 to 5, we have a positive slope. Okay, so those are the signs of our G double prime. What is the other name for G double prime? F prime. You could use them interchangeably. This is also F prime. Okay? All right, so inflection points, what do we have? 0 and 3. We have 2 of them, don't we? We have x equals 0 and 3 because why? G double prime of x changes from, or just changes sign. We don't even care which way from on this one, right? Not on this one. Come on. All right, so changes signs. Okay, how are we? We okay? All right.